Welcome everybody. It's my great pleasure to give a talk during this workshop on quantum machine learning. So I will be speaking a little bit more from hardware perspective, since I am both physicist and electronic, and also a kind of computer science guy as well. So the title of my talk is Towards Quantum Neural Network Implementation in Semiconductor Single-Electron Devices. So I'm working on this topic with my company, Quantum Hardware Systems, and also this was the topic I developed at Łódź University of Technology. So let me move on. Right. So I will briefly give us the current status of quantum technologies available. I will address the need of quantum neural networks. Actually, I will come back to some original ideas of implementation of quantum neural networks from hardware perspective. So my philosophy is from hardware to software. So usually it's opposite to most of methodology, since dominant methodology usually is from software to hardware. Then I will I will specify some properties of semiconductor single-electron devices, since this is very promising family of solutions that can replace Josephson junctions that are currently in use, and as with Qiskit and other technologies. In this context, I will also mention about quantum graphs, and then I will give explicit solutions and equation for the case of two single electron lines, and this is because in the formulated quantum neural network problem, I have n interacting single electron lines. So this is just generalization. And then I will mention about something about nonlinearity, which emerges from quantum mechanics, that is a linear, which actually emerges in the case when in n-body system we only perceived one particle. So then this one particle is governed by a kind of nonlinear equation, and I will just mention the methodology behind such picture. All right. So basically, you know, you all know the principles of quantum mechanics, which is encoded in a superposition of states. This is actually also a feature of classical statistical physics, that this parallelness is built in. And there is an unusual feature which is mostly reserved for quantum mechanics. That's a quantum entanglement. This is non-local correlations that expresses non-local correlations, and this is resource for quantum computation, and this is the resource which is used, which will also occur in quantum neural networks, and their possible, let's say, advantage over the classical neural networks. Then of course, if we design the technology from the chip point of view, we need to be careful about decoherence processes, and as you see, one of the paper by Daniel Loss, he from last year on semiconductor quantum dots, they start to do better and better, and they approach the lifetime of quantum states similar as in Josephson junctions that are used in IBM quantum experience. Then there is, of course, interference phenomena that occurs in quantum mechanics, and this feature of movement over many paths at the same time. So in the context of previous discussions, I can also say that it's not surprising that quantum machine learning is a bit encoding, has similar capabilities to classical statistical physics expressed by classical machine learning, because somehow those theories are interconnected. Okay, let me move on. So basically, we have various types of qubits implementations, more than 20 existing technology nowadays. Here's the brief sketch of Josephson junctions that are used. So there is a superconducting nanowire interrupted by non-superconducting strip. So this is picturized by X sign, and then there is a possibility of tuning of physical states. So So there is a quantization of energy levels in washboard potential given on the right. So this is the technologies which we are using mostly right now. Actually, right now we are using Transmon qubit that is specified on the next slide. So before that, um, before coming to description of Transmon qubit and then its reference to semiconductor single-electron devices, I need to give a brief introduction to superconducting Cooper pair box. Essentially, we have a small superconducting island. On the top, there is insulator, and on the top of it, there is a bigger superconductor. And this small superconducting island is in proximity to metallic plate that is charged. So then this charge present on metallic plates push out Cooper pairs from this small island. So this incorporates this Cooper pair box that's specified here. But this system has had quite a lot of noise in itself. So then it was enhanced, and then the Transmon qubit has emerged. So in a Transmon qubit, you have bigger superconducting island, two insulator materials, and there's another superconductor, and this is tuned by external metallic plate. So here, actually, electric field is used for controlling of the quantum circuit as well as magnetic field. So two fields are used. So that's this enhancement, and this qubit has quite low noise, and therefore it's kind of commonly used worldwide right now. So there are various variations of this qubit. I'm not going to describe, but then there's also possibility of having this interface between Josephson junction, so superconductor, insulator superconductor versus semiconductor quantum dots. I will refer to this slide a little bit later in my discussion time. So what is the topic of my interest for today's presentation is chain of semiconductor nanowires that are in gray, and on the top there is a metallic gate that is separated by insulator. In such a case, you can define programmable two-dimensional metal lattice. So you can block the electron transport across certain paths. Actually, you can even encode a kind of like metric, like coming from, let's say, from general relativity. So you can create bounded states, but also when you look on the system closer, you can recognize certain injectors as inputs of your quantum neural network and certain injectors on the right side as outputs. So also this system can incorporate neural network as well. So this is quite unusual feature, which I'm going to discuss a little bit later. So this is typical artificial neural network. Essentially, I would say what is the essence of artificial neural networks is this interconnectivity of layers. It can also be later translated by strength of so if you imagine this is a physical system A, this is physical system B, then there is physical system C, and this is physical system D. Then this interconnectivity also can be expressed by interactions. But what is the essential part of artificial neural network is that there is nonlinearity built in, and I will explain a little bit later how to come out with this nonlinearity in real physical system. Okay. Then next slide. Yeah, and then now people are having more and better lithography techniques, so they're able to build smaller and smaller nano-sized systems. So basically, we can attempt to encode a neural network that can be both classical and quantum by means of semiconductor quantum dots. They are very well scalable. So, like the recent transistors, for example, there is interconnection between source and drain in the range of 5 nanometers. So this gives you possible big density of information that can be present in such systems. So I'm just giving briefly the insight into that. Yeah, so basically we've given lattice. I can attempt to have a classical and quantum artificial life implementation, like kind of Conway quantum game of life. I can have a quantum communication, and metrology and quantum computation. I will focus today on the quantum neural networks, and also I can think about implementation of hybrid classical quantum algorithms in that type of system, and of course, I can translate other physical models to this two-dimensional lattice model. Okay, so if we see the current status of superconducting technologies, there's more than 20 already existing technologies. But from the point of view of really big industrial applications, the most serious seems to be superconducting technology that is already in use, and there is but there is a problem with superconducting technology that it has saturation of. It cannot be downscaled because the size of Cooper pair in a superconductor is in the range of 300 nanometers. So that's why you cannot make very small transport qubits. Um, so and this barrier can be replaced by semiconductor quantum dots, or so that they are already in big development. But of course, not yet they have exceeded the performance of superconducting Josephson junctions. Of course, you can also think about hybrids. So this motivates me to go for a quantum dots or for possible interface between quantum dots and Josephson junctions. And here is the scheme of possible quantum neural network. So by red dots, you have the semiconductor areas. So the electron is localized in those regions. And basically, the interconnection is expressed by orange. And on the top of it, there is metallic electrode that is separated by insulator. So these metallic electrodes, they control the connectivity of this neural network. So you can reprogram its shape quite dynamically. So that's a feature. And basically, having the injection of free electrons at the same time, then they can propagate their structure, and then they can arrive into detectors. So this is one of possible scheme. And then this problem becomes naturally the problem of quantum transport across the structures. Here there's something like layers, but this layers makes also a kind of complications from the point of view that those wave functions intermix. So you can also think about disconnecting of these interlayers. So the system becomes a little bit simpler in its description and its steady. Right. I will maybe answer to these questions at the very beginning, at the very end, about the curvature. All right. So let me move on. So this is my motivation factor, motivation starting point, and then I will just briefly give a scheme of methodology that can be used in its description. Then, if we talk about even from the picture from before, so let us see certain thing. So if we here on the right side, let's say, let us cut this interconnection in between. So let us make very big barriers by setting certain voltages to C1 and C2, C8 and C5. Then basically the system will start to be visible as single electron lines. And so they will be weakly coupled. Otherwise, the interaction between them, they will be strongly coupled. So now I will try to see from a physics point of view how to describe the systems in greater detail. So, okay, and this is on the next slide. So basically, the suggestion is that you have like three, in elementary particles, you have scattering problem. So you can have incoming particles when they try to collide or they're close to interaction. So when they're very far away, they don't see each other. So this is how you're supposed to see three inputs as three independent qubits or weakly interacting qubits. Then they can interact with big ensemble. I call it soup of n interacting particles that are controlled by some signals. And then at the output, you have three qubits that also follow the same pattern of inputs. So they are weakly coupled one to each other and also moderately coupled to this assemble. So this is basically the scheme of devices. So this is how to translate this problem to n-body physics, and then quantum physics, of course. Then there is also the case of simplification of a system from the left, when you, like as I already mentioned before, you have separated this the big soup of interacting particles into actually n coupled inductively or electrostatically coupled single electron lines. Then you have the structure on the right side. So you have relatively weak interaction. And this is actually this here, the concept of single electron wave function that is perturbed by presence of other electrons can be valid. On the left side, however, this perturbation framework is no longer that possible, especially in the medium area. So this is two pictures which you could think on. And of course, it's somehow better and simpler to start from the right picture. Okay, let me move on. Okay, so this idea of neural networks. So there was idea of neurons, artificial neurons, is not that young. It's 2002. It was first proposed, but actually I could not come across big implementation of quantum neural networks among big players as Google or IBM. So that's also surprising. What is the obstacle in doing so? But because of potential of companies as NVIDIA and others, I think this hardware design of quantum neural networks is very important, both from applied point of view and also from fundamental science point of view. And I'm also raising this question: how better is quantum neural network performance in relation to classical neural network performance is very important question. Okay, so now I just want to give you very elementary toy models because I don't want to float you with too many equations. So imagine that you want to implement AND gate, and that imagine that then you have position-based qubit, which means that it's or bit, let's say. So if electron occupies half of this space over here, it has logical 0, and in another part is logical 1. And then so you have 3 electrons in the semiconductor areas that are in yellow. And then if you place 2 other electrodes that are positively charged, then also you also can have so you have electrode system. So this is 1, 2, 3, 4, 5, 6, 7, 8 electrodes. And with such framework, you can implement AND operation. I just remind you as exercise. And then the first situation is thinking by framework or of classical physics and Coulomb interaction. So this is like charge balls philosophy. You can think about the solutions of this problem of specified here that will come. And here's the following scenario. So if there are 2 inputs and then the electron is at the end, which incorporates logical 1, 1, that this will generate you 1. And here is negatively charged electrode. Then if electron is here and here, remember, there's always repulsion between the charges of the same sign, and attraction if the sign of charges is of opposite. Then if one electron, one input has logical 0 and another has logical 1, then you have 0 at the output since electrons is in this position. And then you can have a situation when there is 1, 0 at the input, and then you have 0 at the output, and then when there is 0, 0, and there is 0 at the output. So you can design such a gate with proper geometries in the framework of classical methodology, and then you can go for a quantization, and I will mechanisms, and I will give you description how to do it very briefly. So yeah, and I will come to with the questions on the next slide. In the meantime, I also mentioned that my methodology is very compatible with CMOS technology, cryogenic CMOS technology that develops very rapidly those days, and that therefore it can be used by a semiconductor industry. So here is a position-based qubit, so which is between 0 and 1. So the presence on the left quantum dot is 0, and on the right quantum dot is 1. I'm sorry for I'm sorry for for a yes. So here is this situation of this position-based qubits, and so this is position-based qubit expressed on the left side. And when you want to do a logical negation, you are using simply the fact that if you have charge in a box, in one box and another box, the charges will tend to be opposite with maximum distance due to Coulomb repulsion. So the system which is described here is natural expression of NOT gate that you can implement in devices. And also you have source and drain in transistors, so source can be recognized as one quantum dot and drain as another quantum dot. So that's how it's related with technology. Okay, so let me move on. Yeah, so you can express various gates and architectures in the framework of lithography techniques. Yeah, and then you can have also programmable quantum graphs, since you can, as remembering this lattice, meta-lattice, two-dimensional meta-lattice of quantum dots, as meta-lattice of nanowires, you can cut certain regions, so you can actually program quantum graphs in a real time. And basically, if you have a quantum algorithm expressed by a graph, I can translate this into physical signals. All right, so let me move on. Yeah, so and then there is a Vannier qubit, this position-based qubit, which I mentioned before. So it's Hamiltonian, and so essentially it's two-dimensional. It's like spin-like Hamiltonian. So there is energy associated with presence on the left and right quantum dot, and there is some Hoping term in between. So this is Hamiltonian for a single two quantum dot system expressing one position-based qubit, and this is related with eigenenergy qubit is commonly used because in typical eigenenergy qubit you are having the linear superposition of two energy levels, and this can be directly translated to this Hamiltonian or to this matrix that is basically similar to spin in a magnetic field matrix. And the translation is expressed by R coefficient. So here are wave functions psi1 and psi2, which are eigenvalues of Schrödinger equation for first and second energy level. And then there is integration. So basically this is very, you can go from position-based qubit to eigenenergy qubit, or from eigenenergy qubit to position-based qubit. So the minimum kind of expectation is that at least two levels of energy are occupied. So then this information is compatible in both systems. So you can also deal with various curvature of cables. And then what is interesting, you have a system of two interacting particles. This is expressed by such a Schrödinger equation. So this is the system. So we have confining potentials for first and second particle and interaction Coulomb term encoded over here. What is interesting that with bending of cables, there's a kind of like dissipative term that emerges, and actually it can be formally translated into complex value vector potential. From physics, we have a real value potential, real value vector potential, but due to this non-zero curvature of the cables, this potential can become complex value. All right, and then in case of two quantum system interaction, two qubits interacting, you have such Hamiltonian. And so just to remind you, if you have n single electron lines, this picture will become this picture will become more complicated. It will be like matrix 2 to the power of n times 2 to the power n. So this is just a kind of simplest case. So this means that basically quantum neural networks, it's quite difficult to model the quantum neural networks that has more than 10 inputs. So you need to use a kind of classical methodology to do it. All right. And then there's a prescription how to have these coefficients Q1, Q2, Q3, Q4 which express Coulomb interaction that are given over here. So basically we can incorporate. So the thesis of this work is as following. If you have a classical neural network, I can encode it in charge-ball philosophy, and having this encoded in charge-ball philosophy, then I can also quantize it and go into a quantum picture. But I cannot deal with more than 10 inputs due to the nature of complexity of system. Nevertheless, it can be expressed experimentally with as many inputs as you like. So that's also a feature of experiment that can go beyond theoretical picture. So I can also express basically any quantum of algorithms by equation 7, and then incorporate this in neural network. My thesis is even stronger. I would say that recurrent neural networks can incorporate most classical algorithms, and if I have a quantum recurrent neural network, I can most likely incorporate all quantum algorithms as well. Yeah, so there are some features of ground state. Maybe I will skip it, and then I will just to form you the final message. So you can also start the description of this problem in terms of classical Hamiltonians. So here's an example of some simulations done by student Piotr Miński from Łódź University of Technology. He did fellowships with Quantum Hardware Systems Company, and then basically he expressed OR gate by such classical Hamiltonian of two interacting particles. So here's effective potential, and then two particles were injected and the input, and then so this is the framework, methodological framework known to people dealing with physics or mathematics. Then also you can do such things for XOR gate, also express classical XOR gate by terms of classical Hamiltonians, and then you can go for its quantization later. So, and then also there is interesting that two previous pictures, if you perturbed by noise, then you can have family of trajectories. And then actually this family of trajectories can generate you probability map. And if you use square root of probability, then you can have a kind of wave function generated quasi-classically. So this is like Nelson mechanics. So there are certain interconnections with classical statistical physics here as well. So I can just say that I can basically model both semiconductor quantum dots devices and also superconducting quantum dot devices in this framework. And there is a lot of work in progress. And just at the very end, I will mention how it happens that nonlinear mechanics, because the key argument against quantum neural network is that you can say that Schrödinger equation is linear. How you supposed to get this nonlinearity? And here's a picture of two simulations of two charged particles described by one-dimensional Schrödinger equation. They are trapped in a box. So here are the cases before and after measurement. And then how it's possible. So if you have weakly interacting particles, then you can, for n-body case, you can have factorization of few wave functions of each particle. And then with proper integration, you come into equation 32 and 33. So basically, there is a potential, AB potential, that depends on the wave function of another particle. And this potential will lead you to from integral equation into integral differential equations that are as specified over here. So in that sense, expect that this chain of quantum dots in the framework of a single electron particles has nonlinear feature of nonlinearity that is very much needed in design of neural networks. So this was somehow described the simplest scheme. Maybe now I have a time for your questions or comments. So please, I'm open. Thank you.
Okay, thanks. I see that there are some questions from Sebastian. Maybe I will read it first. Why and what kind of curvature do you mean, and do you plan to use some symmetry patterns in your device? So this is the first question.
What kind of curvature symmetry pattern? So okay, so I already used this device which is given over here. Okay, so let me come back. So it's possible to model like gravitation center, for example. So you can build a metric. One second, where is that? I need to. You can build a metric. Yeah. So this is this slide. So you can program any type of two-dimensional metric you like, basically. So you can simulate kind of gravitation waves, or I mean, basically the system of interacting bodies. And what is also interesting, you can also I mean, let's say, model the bounded molecules. So you can have certain charge over here that plays role of nucleus, and there will be electron that is on bounded orbit. So you can basically, with this system, you can implement two-dimensional chemistry. That's my message. Did I answer your question or not so much?
Yeah, it's enough. Thank you.
There is a MDPI paper, materials 2024. So please just type MDPI Pomorski materials 2024, and you will find more reference. Or I can send you this paper to you directly.
Thank you. And what with symmetry? Could you apply some kinds, very special kinds of symmetry for
yes,
your...
I guess so, right? I mean, I can also polarize. So I can, for example, apply rotational symmetry by some voltages applied to it. So I can basically have a pattern of periodic or non-periodic pattern. It depends on your needs. So I definitely have such possibility, I would say.
Okay, and yeah, thank you. That was my question also for this, because you define weak and weak interaction and very weak interaction. But as I understand, at this level, at this quantum mechanical level, you just have a kind of electromagnetic interaction. Just
well, the problem is that here on the right picture, if you have separate lines, you don't expect that the electrons will jump you from one line to another line. So in the picture on the right side, you can omit spin degree of freedom in description of electron or holes. Actually, it can be also for holes, moving holes as well. But in the left picture, you cannot ignore a spin presence. So the wave functions will intermix. So what consequences will have? So you have three separate wave functions injected. When they propagate, some wave function of first electron will be partly present here, here, and here. So it can be fractionalized. First charge can be fractionalized at the output, right? And this is the same with second and third wave functions. So this will be complete intermixture of wave functions. So that's why this picture of strongly interacting single electron lines expressing quantum neural networks, this picture is, I would say, more involving theoretically. And also, if you are involved with n-body quantum system dynamics or even classical system dynamics, you know that n-body picture is without mean field approximation is challenging. Basically, it's challenging in modeling and in analysis in general. So this system is will have this systems will have will be more complex. So I can analytically I can tell you I can pre-design quantum neural networks of the right system much more easily than the left-right system. because there's certain intuition of charge balls which I can incorporate in the right picture in a weakly interaction with these gaps in between. But this picture might be broken in the situation on the left side. So that's not that easy, but it's a nice research for future, I would say, right? So that's nice vision for some future study.
Okay, it's just one last question, sorry. Because you said something about this holes with electrons. Is possible maybe take some effective kinds of particles different than electrons in this device?
Absolutely, because let's say what is electron is lack of hole is a lack of electrons. So this hole can move back and forth. Let's say, okay, so you can inject holes as well. So they have all features of electron, except the fact that they charge the hole. The hole charge is opposite to the electron. The spin of hole is opposite to the electron. And when the electron meets with electron and holes meet, they recombine. So this is like annihilation. So in a very real way, hole is almost like antiparticle to electron. But from equations point of view, the equations are actually almost the same. So the same concepts will apply, basically. You can have also a situation when you inject hole and electron. You can also deal with such situations. There is some study of Dirac Q company from Australia, because they're one of the best in the world in this direction, research direction. So they also start to use hole more often than electrons, actually, for certain experiments. So both particles are possible, but it's rather recommendable to use only one of them. So it's better to decide to use holes or better to decide to use electrons.
Yeah,
it's also
because I just remember that you can have, for example, perovskites that the topological information about holes and electrons can give you some new opportunity to do something more with that. So yeah, this is very, very interesting.
Well,
Thanks.
electrons and holes, they occur in Andrew-bound states in Josephson junctions, so they're both present. So if you have equations, Bogov-Dijon equations for Josephson junctions, then you can. By the way, if we already touched the Josephson junctions, there is a lot of nice work by D-Wave company expressing superconducting classical Josephson junctions using. So you can implement classical neural networks on Josephson junctions. It's already done. But what is the feature of this work is small size of neural network and possible quantumness. So there are two things that I can address. But even if this network doesn't fully work in deeply quantum picture, it can still be parameterized, used for a quasi-classical neural network. So that's a nice feature of that. But of course, a quantum neural network will have better possibilities, and especially when you integrate it with, for example, with quantum detectors, then if you have some information storage in quantum detector, it cannot last too long. It needs to be pre-processed. Yes. So this is one of area of application of quantum neural networks. Did I answer your question?
Yeah. Thank you very much. It is very, very interesting for me. Thanks. And we probably has also a question from Jacob. So
yes,
maybe.
yes, there is one question from Jacob. The question is, how would your solution compare in terms of performance and function with optical neural networks or neuromorphic chips?
I would say I somehow already described neuromorphic chips more or less in that way, because okay, you can also couple this system to some other systems, so there could be some information storage and so on. So somehow this methodology expresses neuromorphological systems. What was the second part of the question? Pavel, what was
optical neural networks.
Optical and neuromorphic chips.
Optical. Well, there is a competition, so people start to go. They can use photons instead of electrons. So there's a competition. I would say the photons has okay, so like there's a quantum optics in quantum information processing present, right? And the problem is that it's hard to make two photons to be interacting with each other. On the other hand, they can interact, for example, via a nonlinear medium, for example. But on the other hand, they have long time of life. On the other hand, electrons are strongly interacting and are scalable, but don't have very long time. So there are advantages and disadvantages. So it's hard for me to answer this question in greater detail. I think one need to do more research on that.
Thank you.
Okay, thanks. All right.
Anything more?
Yes, I do not see more questions on our chat. Would maybe someone else would like to ask? Perhaps the last chance. All right, I don't see more questions. So Krzysztof, thank you once again. First
Thank
of
you.
all, for the great presentation and for answering all the questions.
Thank you.
And